All right. Welcome to the RV 2021 award session. I have the great privilege of chairing this session. We have two awards that will be announced today. So this is the Best Paper Award for this year's conference. The Best Paper Award, of course, recognizes a very outstanding paper among the many outstanding contributions to this conference. And we'll also announce the Test of Time Award, which recognizes a paper based on an early edition of RV. The eligible papers are from RV editions that are 10 years ago or even before that, including the time when RV was a workshop. And of course, the Test of Time Award recognizes papers for their high impact they have left on the community. Okay, let's get started with the RV 2021 Best Paper Award. Maybe a quick word about the process. So the way this works is that the PC chairs choose candidate papers based on the reviews and the discussions, and then pass these papers to the award committee. This year, the award committee consisted of Martin Leuke, Dave Parker, and Bernd Pellet, and they reviewed the papers, ranked the three, and justified the scores, and then they discussed and eventually reached a consensus which paper should be awarded. And now, without further ado, this year's Best Paper Award goes to Predicate Monitoring in Distributed Cyber-Physical Systems by Anik Momtaz, Niraj Basnet, Hussam Abbas, and Borzo Bonatapur. So congratulations. And maybe you guys could turn on your cameras so that we can clap for your benefit. I see Borzo is already here.
We're here.
Yeah, so congratulations.
Thank you.
Thank you.
Thank you.
Outstanding. So I have a note from the award committee that I would like to read. The paper tackles a challenging problem for distributed cyber-physical systems, namely how to perform runtime monitoring in the absence of a global clock and in the context of analog signals and continuous time. This is an important and highly relevant problem with many practical applications. The technical contributions of the paper span both theory and practice. These include a novel theoretical formulation of the problem and an efficient SMT-based solution method. The authors also show impressive experimental results from applications to both real-world and simulated cyber-physical systems. The paper itself is of an extremely high quality and presents the contributions clearly and effectively. Well, so congratulations to this outstanding work. Thank you very much.
Thank you.
Thank you.
All right. Then let's move on to the Test of Time Award. The Test of Time Award exists since RV 2018. So here, the way this works is that the PC chairs select a large number of papers from, in this case, RV 2001 to RV 2011, based on citation counts per year. And then there's an internal selection committee consisting of 5 members that scores these papers. The 3 with the best scores get passed on to the external selection committee, which this year consisted of Alan Hu, Marta Kwiatkowska, and Fabio Somenzi. And the external committee then decides on the winner based on individual ranks and justifications, followed by a discussion until a consensus is reached. So the RV 2021 Test of Time Award goes to Parametric Identification of Temporal Properties by Eugene Azarin, Alexandre Donzé, Ored Mahler, and Dejan Nikovic. Congratulations.
Thank you.
Thank you.
So again, I have a quick note from the award committee to read. We were presented with a very strong set of nominations, but converged on this paper for a number of reasons. It goes without saying that the work itself is of very high quality, It introduced PSTL, a parameterized temporal logic with dense time and real valued signals. It poses the inverse problem of parameter identification, a class of problems of growing importance. It develops the theory of two different methods to solve this problem. And it presents preliminary experimental results with two different implementations. Committee members particularly liked the framing of the parameter identification problem and the balanced blend of theory and implementation. From a test of time perspective, we also evaluated overall impact on the research community. Here, we noted that even just the formulation and introduction of PSTL alone has influenced a large number of researchers in the community. Putting this all together, we were happy to select this paper for the award. So congratulations again. This has been a really meaningful contribution to the community. And I'm very happy that the winners of the Test of Time Award will now give a presentation. So I understand, Dejan, you're going to start, and then Alexandra, you will also give the talk today. So I would suggest, without further ado, let's move on to this presentation.
Yes, thank you very much. Actually, when we learned about this award, we were extremely honored to receive it, and it has been a very emotional moment for us, and it's a huge pleasure to be here in this role. And what we are going to talk today, so what I will start digging a bit down the memory lane and trying to remember how we came to this idea and what was the context in which we were thinking, what was our mindset at the time, and then Alex will give actually the original talk that he gave in San Francisco in 2011, and then we will talk a bit about how this work impacted us and what were the lessons that we learned from the perspective of today. So let me just say a few words about the authors in 2011. We have Evgeny Asarin, who was at Liafa and is still in Liafa, except that the name changed of the lab. It's IRIF, I think now. Unfortunately, he could not join the beginning of this talk, but he will join a bit later. Then Alex, who at that time was in between his two US adventures. So he was in Verimag. Oded Mahler, who was the supervisor of both Alex and myself who was a postdoc in IST Austria. So before talking about the context in which we thought about this idea, I would like to just remind what was the meaning of runtime verification at the time that this idea slowly started to grow. And I went back to the first workshop on runtime verification 2001, and I just copied two sentences from the webpage on what the steering committee at the time thought about the field. So it was actually a nice way to look back also how was it defined in the very beginning. And it said the objective of RV01 was to bring scientists from both academia and industry together to debate on how to monitor, analyze, and guide the execution of programs. The ultimate longer-term goal is to investigate whether the use of lightweight formal methods applied during the execution of programs is a viable complement to the current heavyweight methods proving programs correct, always before their execution, such as model checking and theorem proving. And I stole this very nice picture from the tutorial on runtime verification by Elias Falcone, Klaus Havelund, and Giles Reger, that basically shows this basic setting of runtime verification, where you have your property, your spec, and then you generate a monitor out of it, and the monitor is interacting with the instrumented system by observing it and possibly giving it feedback, and then giving also a verdict whether the property is satisfied or violated. So what we can see from the previous definition, I think at the very beginning there was this focus on programs. So this was probably the initial motivation, and I guess Klaus or Oleg can tell whether this is true or not. And also there was this implicit focus on during execution, because after all, the name itself, runtime verification, somehow suggests that the interesting part is to observe the program during its execution. And what I actually like also, the fact is that it was kind of a humble position, where they're not claiming that the runtime verification is the solution, but it's like an investigation of whether this can complement the other methods. And what was also interesting to me is that the steering part, and we have heard about runtime assurance and so on, is present from the very beginning in the RV community. So before Alex or myself even started our PhD, or we probably even thought about science, our mentor, Oded Mahler, started to be interested in what he used to call the barbaric verification of hybrid systems. So as many of you know, Oded's field was hybrid systems, and in some discussions with him, it was around the end of 90s, beginning of 2000s, where he realized that the reachability analysis of hybrid systems, so one of his major topics in his career, has and will have serious scalability issues. And at the same time, there was the beginning of this success of assertion-based verification in digital hardware that actually also Sanjit mentioned 10 minutes ago, where people like Dana Fisman played a big role, and there was this four-spec language from Intel with, for instance, involvement of Moshe Vardi, and the competitor language Sugar from IBM that were developed in parallel, and there was the merging of the two that eventually led into the IEEE standard property specification language like PSL, and then system Verilog assertions. And at that time, Oded heard about this assertion-based verification by people from this Dolphin Design company, which is a small EDA kind of company in Grenoble. And this was kind of the basic idea that where Oded starting thinking about this direction for hybrid systems, so for the systems that have also this continuous dynamics. And this led to the constellation where Oded started two PhD theses. So actually found students who started working on two PhD theses. So Alex started in 2003 with the simulation-based verification of hybrid system, where the question was, can we use a finite number of simulations to formally verify, to provide some guarantees about the system? And 1 year later, I started the PhD on specification-based monitoring of hybrid systems. So basically, can we use the runtime verification like technology for systems that have this kind of continuous dynamics? And then there was an omnipresent figure around the Verimag laboratory by Evgeny Asarin, who was one of the big collaborators of Oded, and he also used to work for a long time in Verimag, and who was always giving this touch of wisdom and the rigor into our sometimes chaotic thinking. So yeah, this was basically the setting around the mid of 2000s. And what was our take around mid-2000s on RV? Actually, we were not so much familiar about the RV community. We were more around this analog mixed signal circuits, more around the formats, timed system community. And what we wanted to do was to use the monitoring techniques to support the design of mixed signal integrated circuits. So we were focusing on what I would call offline runtime verification, which is kind of an oxymoron, but that actually we will show afterwards that it's kind of meaningful. And the main reason to use the runtime verification monitor for us was as kind of a testing oracle that replace the analog designer looking at the waveforms and deciding whether they conform to the spec, but having this process automated. And also what was probably different from most early works on runtime verification, although this is also not completely true, is that we were considering these real valued and dense time behaviors as inputs, and not like a sequences of event, which is kind of more, let's say, the more common runtime verification work at that time. And this is kind of important for the rest of the presentation. So around 2010, around the time where we really started working on this topic, what was the landscape? So in 2004, Oded and I introduced the signal temporal logic as the specification language for reasoning about the system that combined the discrete and the continuous dynamics. And we provided like a very simple also quite elegant offline algorithm, monitoring algorithms that was based on direct manipulations of signals, so without using the automata. And then the next big, I would say, step was done by Alex and Oded when they equipped STL with the quantitative semantics and proposed this offline robustness algorithm. And we have heard also, I think, actually the tutorial of Sanjit was kind of a nice introduction about the impact of this kind of things. And in the beginning, our thinking was we wanted to conquer the mixed signal IC design world. There were still some other applications that started evolving, like system biology, but really analog mixed design was our target. We had at that time some positive feedback from the semiconductor industry. So we did some case studies with Rambus, with ST Microelectronics, Freelance, Mentor Graphics. Some of the people started citing STL work, but it's still very, very preliminary. There is nothing big going on. And actually it will turn out that the real success will come later. And one of the main ingredients was this addition of the quantitative semantics and moving more to the CPS application domain, and rather than the analog mixed signal, which was our original target. So in 2007, I had kind of a reality check that all this conquering the world was put a bit back on the ground when I was invited to an internship to Rambus. And probably many of you don't know what Rambus is. It was like a Ferrari of memory interfaces. So if you had a PlayStation or a high definition TV, there there was some intellectual property from Rambus on fast access to the memory and so on. And at that time, they had a very, very nice group that was supporting a lot verification of hybrid systems community through internships, through projects and so on. And they brought me to Rambus to try all this specification-based monitoring. And we had the very beautiful idea. The designer gives us specs and the design. We do the simulations. We check them with our RV monitor, and we save hundreds or thousands hours of manual checks, and everybody wins. But then immediately we are what I learned there is first. They do not usually have formal specifications, nothing even close to this, but also even if they have some kind of template ideas of what should happen, they don't have this timing or amplitude parameters. So basically what they told us is, what they told me is, look, we create like a basic design, like a concept design with some basic physics, and then we simulate, and then we infer. We try to see what are the meaningful parameters, and there is this kind of parallel process of doing the refinement of your design and completing your specs, which is not what we learn, that you start from the specs and then you derive your design out of it. And this was the seed of the idea. Actually, at that time, I don't know how I managed to convince Dad, but he paid my trip back from the States to Salzburg for a week to attend the Formats 2007. And we first discussed about this idea, but at that time it was kind of a vague, you know, dinner-like discussion that we put under the carpet. So basically, I was finishing my PhD, so I had more urgent things to do. But Oded used to keep this one-page drafts that he would like take out after 10 or 15 years, and actually end of April 2011 we revived this idea, and actually Alex managed to find the email where we first decided to work and to formalize this idea, and we formally formulated the problem that we wanted to solve, which was basically, I just take this from the paper, given a parametric STL formula, find the range of parameters that render the formula satisfied by a given set of traces. And now I would like to give the floor to Alex, who will present the original paper.
Yeah, okay, can you hear me and see the slides?
Yes.
Okay, cool. Yeah, thanks again for setting up the context and the historical notes for these works. And I have to reiterate myself too that I was very honored when I heard the news of this reward. So I want to tell you a little bit more about the paper, and so we chose to give the original paper presentation. And the main reason, of course, is because I'm lazy. So I just reuse slides like everybody else, I guess. But so when I gave this talk originally, when I was left with an impression of a lukewarm reception from the audience, like I was not so thrilled by the talk. And when I look back at the reviews, actually, the three of them, they found nothing wrong in the paper. One was nice enough to strong accept it, so we got in a good position. But actually, they all had very low confidence, just they gave medium confidence. And so that's one reason, the other being that the talk was certainly not great, but another reason why the audience didn't stick maybe to the topic is when we think back of at the time, well, STL was still young, and systems, I mean, they were not a familiar topic to the RV audience yet, clearly. And also, this is a paper about learning, which we maybe didn't completely realize at the time. And learning was not yet all the rage that it is today. That trend would take off a couple of years after that, like in 2012 or 13, around that time, where deep learning would really take off. So that explains maybe the reception, the original reception. So I thought, okay, let's give this presentation another chance. So here we are in 2011, no COVID, in San Francisco, and talking about parametric identification of temporal properties. I wouldn't even mention STL yet, with the author that they have presented. And the first slide is maybe where I lost my audience already, because I don't know why I put a differential. Let's see, a differential equation in this. This one, yeah, I don't know what I put this here. And in the audience, I don't know how many people knew about the differential equations at the time. We're not used to that. But like Dan said, hybrid systems were the main topic that I had been working with Oded. And so they create those kind of traces where we have dense time signals and real valued components. And so we're talking about STL properties, which is an example here. And really, this paper it is based on a very simple idea that the numerical constants that you have in an STL property, we can replace by parameters. And this is how we define parametric STL formulas, parametric STL. And we want to solve an inverse problem. And now really we should not say inverse, but like machine learning problem, I guess, where how do we assign values to these parameters so that the formula that we obtain is satisfied by a given signal X. And here, okay. And so the outline of this talk is nice. I'm introducing PSTL more precisely, except that I'm not actually talking about PSTL, but anyway. And then I'll present the two methods that we presented in the paper. So, and as is often the case for like verification papers, we have an exact method that does not scale, and we have a barbaric approach that does not prove anything. So I will be talking about those two approaches. So I had to talk about STL, and first I had to talk about signals. And in this paper, we gave formal definition for the signals. We just assumed that we had piecewise affine signals. That is, for each time segment, we have an affine equation with given parameters. And signal temporal logic is, I was introducing it as a goal of specifying temporal properties of signal. And we're all familiar with the syntax now. And we have Boolean operators and temporal operators, which is the until. And I was giving the semantics here, and maybe I lost another part of the audience there by just throwing this here. But now it's people are probably more familiar with this. So we have like predicates, Boolean operator, temporal operators, and the eventually and always. And PSTL, we have what we called space parameters here and time parameters, which are those A and B's there. So I was giving an example there. So here is one signal. If the formula is just a predicate, if we evaluate it at different times, x greater than 2, so clearly it's false here. Then we get greater than 2, so it's true. Then it's false, and there's a small period here where it's true. And eventually x greater than 2, so it's true. So this is true until it is not. Eventually it is bounded eventually, so etc. Okay, so and this paper really is about replacing those constants here and there by parameters and finding values for which it is satisfied. So for example, this eventually 0, 0, 5, so it's not satisfied because at type 0 it's not satisfied. So you can even you can either change 0, 5 into, for example, 1 here. This will displace the truth, this to 0, and then we'll make it true. Or you can change this constant 2 here and make it, if you decrease it here, then it will make the formula true. And that's really what the methods in this paper are doing. Right. And so in the first exact method that mostly Bernd came up with in this paper is by defining what we call validity domains. And the validity domain is just a set of, it's exactly what we want to find with the ideal solution of this problem, which is the full set of all parameter valuation, such that for each valuation, the formula is satisfied by the signal. So it takes a signal X, a PSTL formula phi, and it's the set of all the valuations such that the signal X satisfies the phi at evaluated at P and S. Okay, and to visualize that, the simplest case is for just a predicate, so S greater than P. So this is the simplest to explain. And if you look at like the first, you can go segment by segment. So from 0 to 2, the set of values of P for which the formula is going to be true is just above just this region above the signal. And then you can go there, and this gives you your validity domain, which you can express by a set of constraints. So the first constraint says, okay, I'm in this time interval, and I have an equation for this domain, or I'm in the second set here, and I have this equation of depend of P and T, or I have in this segment, etc. And with this, we have complete expression, exact expression of the validity domain of the predicate X greater than P. Okay, and then we came up with an inductive formulation. So we have the predicate, and then we just have to propagate this domain definition through every operators of STL, and thankfully STL does not have that many operators. So we have predicates. Conjunction is going to be just a union. Negation is going to be the complementary, and for the until, and then we can just write the formula with quantifiers. Okay, and we have it. It's not very useful, so the simple idea is just to use quantifier elimination, and then we have it. Then we just took off-the-shelf quantifier elimination tool and made some experiments, and it turned out to work not too bad. So, and that was one example of a temporal formula, always 0 S1 X smaller than P, which yeah. So this is the expression with the quantifier. Give this to the tool, which I have no idea, well, very few idea how it works. So we just apply that, and we get an expression. Okay. So we set into just trying this for different formulas, and we tried the most interesting formula that we tried is this stabilization property, where whenever X is greater than P, in some time, after some times, it has to be smaller than P for a time S1. So we have 3 parameters in this formula, which we can decompose, and we tested and we verified that we could generate the validity domains for this formula. And we started with we made experiments with the signals with a growing number of segments, and with 8 segments, then we could find the validity domain for the formula, for the subformulas, and the complete formula in a reasonable amount of time. But when you grow the size and you increase the precision of the signal, we could see that we might have some scalability problem, because I mean this is not that many samples, and already with 32 samples, we could not compute the validity domain for the complete formula. Actually, it would be interesting to revisit this method today, because I'm sure the quantifier elimination tools made a lot of progress. But anyway, that was the result at the time. So we said, okay, there must be a way to do it, to make it scale, even if we lose the exactness of the method. So at the time, like they mentioned, I had implemented quantitative monitoring algorithm for STL. So I knew how to, given one signal and one STL formula, which we obtained by combining so one STL formula. Then I knew how to compute the validity. So, so we thought, okay, one thing we can do is to estimate the validity domain by iteratively instantiating the parameters and finding the satisfaction until we are satisfied with the precision of the estimate of the validity domain. Okay, and yeah, again, the motivation is because we could monitor this efficiently, and this is one slide of the time where I was just saying that okay, this gives an idea of the size of the signals and the time it would take to verify satisfaction. So this was scalable. Although you need an exponential number of samples to do it, but still. So one original idea that we had that we introduced in this paper was the notion of polarity, and that would help a lot to make this scale, to compute those validity domain in a scalable fashion. And so the idea of the polarity that Oded introduced actually was that we have to think about monotonicity, right? So basically, we said that the polarity of a formula is positive for a parameter if we increase the value of this parameter, the formula remains true. So if it's true for a value and we increase it, then it remains true, and vice versa. So this polarity can be computed, can be propagated following different rules. It's relatively frequent that a given formula satisfies this polarity property, even though it's not. It can be indeterminate. Like if we have the same parameter and two formula, then we cannot know the polarity. So it's not always the case. But for many formulas and common formulas, then it's true that that we have this polarity, typically. And so what this gives, yeah. So what this gives us is that the validity domain, if it's monotonic, if we have this polarity property, then it's satisfied. That's what one of the bad slides, I guess. It's satisfied. I mean, the validity domain and the rest is satisfied the property of a Pareto and for Pareto front. Okay, and just at the time, it happened that Julien was a PhD student of Oded, and they had come up with an efficient scheme to compute those Pareto fronts. And here is an illustration that will make things clear. Is if this, so the gray area is the exact validity domain. The idea is that, okay, if we take one sample and we leave, and we can check that it's outside the validity domain, then we know by polarity that that everything below is not in the validity domain. And conversely, if we find a sample which is inside the validity domain, then everything above it is going to be in it. And by this way, we can compute a large portion of the validity domain. And by maintaining a set of points this way, so this modeling these points like a small number of points this way, then we can have an approximation of this of the boundary of the validity domain. And you don't need that many samples to compute it. Although that the number of samples still remain exponential in the number of parameters, but that gave us an efficient way of estimating this boundary. And here is a picture of the boundary of the validity domain approximated for the formula that we showed earlier. And if you remember, this would not scale with the quantifier elimination method. It would not scale above 32, I think, samples. And here we computed it for 1,000 samples. I don't remember how, but yeah, here it is. here it was. So, and so that was the conclusion of that talk, that it's a problem potentially useful. So yes, Howard today proved that we were not wrong about this, which is given simulation traces, what property do the system satisfy? And we showed an exact computation of the validity domain using quantifier elimination, less than scale, and numerical approximation with scale is better but proves nothing. And yeah, and that was the talk really. So, like Dan mentioned, so it was relatively simple, but looking back at it, it's clearly there was some elegance in it. It was a flash paper, 1.5 months between initial discussion and submission. That's a record for me at least. 12 pages. Also a record, I think, like less than the allowed number of pages. And but the reason it happened is because most ideas were already there, STL and efficient monitoring, and the multi-criteria optimization. And then we came up with a few ideas such as validity domain and polarity. Although we should mention, like one reviewer said that Aurélien Risque and François Fage had similar ideas before, and they're kind of I forgot. They should be more known actually, but anyway. But the impact, so it was a flash paper, but the impact went clearly beyond what we imagined there at the time. The first was, I mean, very important because so this talk happened in San Francisco, as you may know, and this was also an occasion to me, and I happened to stay just 4.5 years in Berkeley after that. So it's not clear if this would have happened without this paper and this talk. Then once in Berkeley, so that's it's very important for me. Once in Berkeley, there was CAV the year after, and there we met with Joe and Xiaoqing from Toyota at the time. And this is very similar to the reality check moment that Dan mentioned when he was at Rambus, saying that, we have specifications, but they're not really complete specifications, right? And so what I remember clearly what Xiaoqing told me there, I mean, they were experimenting with the falsification approach with STL and everything, and Xiaoqing would tell me, yeah, you know, falsification is nice, but how do you set the threshold? How do you choose the parameters in there? And at first I didn't understand what she meant, but then I thought, well, didn't we solve this problem? And so we had collaboration, and this led to this paper that had a nice influence too, I think. And really the core of this paper, it can be summarized in this schematic there, and you can see that there are two main components there, which is the find param to the falsify algo there, which is, so this is a falsification approach that actually Sanjay talked about before in the tutorial, and the find param is really exactly what we did in our paper that we talk about now. And the idea is that we had a PSCL formula here, and we would find an STL formula that is satisfied by signals given by a system here. We would try to falsify this formula, find a counterexample, add a new simulation trace, and then loop until we're happy with some form of STL formula. And this relatively simple scheme, I mean, had some success because we found a good, a tricky bug in one of an industrial model at Toyota, so they were happy with that. And I think this was really a beginning of a rich collaboration contributed to the adoption of STL in the CPS industry, like with Toyota and with Joe and others. We did a lot of work later, and this actually had another award that maybe you can see behind me, which is almost as nice as this one we're talking about. So, and with many other work in Berkeley that are more or less related to this work. One that I liked is work that we did in robotics and education, where we used this notion of validity domain to synthesize what we call testers for controllers that were designed in the context of an assignment for a robotics assignment for a class. So we had many traces and many with many different behaviors given by students, and all these traces, and we wanted to identify the different critical behaviors and errors that the student would make, and be able to recognize them and test for them for grading the assignment. And then we did a MOOC on that with a few hundred students that we could grade automatically with this. So that was nice. And then further, we also, so the second thing I wanted to mention is to try to introduce model signal STL into the control community. And so we have this paper with Vasu Raman on model predictive control with the STL specifications. And this was influenced by the paper and the notion of exact validity domain, because in this paper we formulate the optimal control problem of the model predictive control scheme using constraints, a set of constraints, much like what we obtain when we use the quantifier elimination, the thing. And of course, today there are lots of active research, machine learning, and explainable AI, where the idea is to try to find STL formulas for behaviors, and with the argument that the STL formulas are more easy to interpret than whatever a neural network can do. Okay, so I will stop here for my personal impact, and I'll maybe give the control back to Diane to finish this talk. Yeah.
So I will say a few words on my own personal impact. Can you see my screen?
Yeah.
So for me, there were three impacts related to this paper. So first, this was my comeback to the RV topics. I will come back, say a few words about this later. This is also the point where I start becoming part of the RV community, which I was not previously. And very similarly to Alex, it's this realization that actually one of the most interesting things about RV are all the questions that are beyond RV. And for the first one, actually, yes, let me come back to the RV topics. After my thesis, I moved first to EPFL and then IST Austria to do my postdoc with Tom Hensinger. And actually, I felt saturated a bit with the thesis and everything. I needed to move a bit away from all these topics, and I was focusing more on contract-based design, on interface theories, and this was, although I did have a couple of publications which were the leftovers from the thesis, this was really, after almost 3 years, the first work where I actively came back to the topics around the runtime verification, and since then I stayed, and it's really my favorite topics. This was my first RV paper. I think this is also the case for Alex, if I'm not wrong. And it was kind of an entry to the RV community, where, as I said before, we were more on this analog mixed signal design formats, like timed automata community. And I have to say that this was an opportunity for me to look back what have I done around the RV community, and there is a lot. So I had the 5 more publications in RV since then. I was given another very nice opportunity last year to co-chair the conference. I was part of the European Cost Action on runtime verification. I had an RV tutorial at the conference. this school. I'm teaching runtime verification at TU Vienna with Ezio Bartocci, and so on and so on. And actually, I made the exercise just to look at my Google Scholar profile to see what are the keywords that I put for my topics. And I realized that this has been like written years ago, so I didn't really remember what was there, and that runtime verification is the first topic, and I'm really happy about this, and I'm proud to be part of this community, and this makes me even happier and even more honored to receive this this award together with my co-authors. For the realization that RV is also beyond the runtime verification, all this work by Alex and by different groups and our work on parameter identification made me realize of how versatile RV technology is. And this is one slide from another presentation in which I show so it's basically how I sell my RV related research nowadays. And I sell it as this kind of basic technology that allows you to do specification based rigorous engineering, both at the design and at the operation time, that links these two worlds, like the design and the operation together. And I have worked since on many topics where I use the basic monitoring technology to do something else, like the trace and system diagnostics, then topics that actually Alex and some other people started way before me, like testing as optimization, testing for sensitivity analysis, and more recently specification mining, where we are not only trying to learn the parameters, but the entire formulas. And this brings me to the end of this talk, where we tried also to reflect a bit on, you know, when you get this kind of award, you try to think what is the reason and what is this community about? And some conclusions that we have is that actually runtime verification is an extremely versatile technology. And that evaluating behaviors is really a fundamental problem. And our lesson learned from, and I think it's reflected in both of our careers, is that one needs to think broad about runtime verification and also about its role beyond runtime verification, because there is a huge and fascinating playground, many things that one can do. And with this paper, we would like to think that we contributed with an epsilon to push this observation that we can use RV beyond RV. And with all these new applications like autonomous driving that we have seen in the previous talk, the DevOps, the continuous engineering, with the complexity of the systems and especially the complexity of the environments, I think that I sincerely think that this community will grow and grow in its importance. And also about this paper, we have, Alex has said it received at the time a relatively lukewarm attention, and but basically one needs to follow a bit our own instincts, and you don't really know where it leads you, but it's usually fun. And actually this paper is a great example from several perspectives. Like first, it started as a constraint solving paper, so this idea about approximating the validity domains using monitoring, it was not there from the beginning. It came there when we realized that we hit the wall, and I think it's Alex actually who first proposed, like, why don't we use monitoring to approximate it. We absolutely had no clue that this work will have such an impact. And actually, if you look at the reviews, we were lucky enough to find the reviews. There was this strong accept, weak accept, and weak accept, which is good, very good. But when you read the reviews, the strong accept said, like, the paper does what it claims and the solutions are illustrated by examples. Okay, it's and one of the weak accepts said, like, the topic and the overall approach of this paper are interesting. Its theoretical contribution, however, is rather small, as the techniques employed are basically known. And I think, you know, I think it's David Lynch who said, when he was asked about interpreting one of his movies, he said he doesn't want to do that because once he releases his movie, it has a life on its own. And, you know, every viewer might have a different interpretation and every interpretation is valid. And I think it's very similar with scientific papers. We had very different ideas about why we are doing this. And actually, sometime later, a different community embraced these ideas, and also it does not come in this isolated bubble. It's not like we have a great idea outside of our context of our environment, but there is this building. There are other groups who started working on STL, who contributed to different parts of this work, like specification mining of STL of Kalin Belta's group, all the work on also falsification testing in Arizona, and it's this community creation around the specification-based analysis of the system that grew also and made the impact of our own work. And actually, for this paper, it came with a certain delay. And with this, I see also that our wisest member of our small group of authors is here, Eugenia Sarin. Would you like to say yourself a couple of words?
Yes, can you hear me?
Yes.
So I'm very honored to be here, and I'm very honored by this award. I'm the first author alphabetically, but in this paper, in fact, I played a minor role that I played in many other papers. I was a mathematical consulting guy responsible for mathematical truth and correctness of definitions.
One could say it's the most important role.
No. Of course, the most important role that brought a test of time to our group, or probably test of time of Concur or to another group, including Audit, was, of course, of Audit as a generator of ideas and the guy who could push these very original and very relevant ideas to a fast realization. And so mostly it's because of him. He had a very good intuition also, as Dayan, you follow your intuition. So probably it comes from that. So I was for me, I discover now that I continue this work, in fact, but I forgot it. I discover now that what we did also with Oded and Duanu Luz, Thomas Ferrer, and Dayan, and Alexei Bahirkin about time pattern matching in spirit. Technically, for me, it's important, and also from the application standpoint, all this time pattern matching story is, in fact, a variant of that.
Absolutely. This is
differently. There were other insights.
I think
there were other
you know that there are these different the parameter synthesis is very similar also to this using the quantifiers in your formulas, and they're very similar approaches. And also I agree with you, all this work on the pattern matching, these are kind of variants of this type of work. And thank you, Eugene, for mentioning Oded, because we have this last slide. It's also an occasion for all of us to remember Oded, who was this driving force and for many of us and who has not been with us now for more than 3 years. And like Jean said, he was also very much the driving force behind this paper. And maybe just one very small comment on what Alex said, that we did this work in less than a month and a half before starting working on it and submitting it, and that this was the quickest paper that Alex did. And actually, I have to say that with Oded and Amir Pnelli, we had a paper that we wrote, actually, Oded wrote in 2 nights. So before the dinner, where we discussed the idea and sketched it, and the submission to leaks, which was rejected, there were only 2 days that passed, and we had a paper which actually in the next resubmission was accepted, and it's a very nice paper. And with that, I thank the audience for listening to our story. I thank very much the organizers of RV and the committees that selected our paper for this award. And we are also very happy to answer to your questions, if any.
Well, thank you very much for this fascinating presentation. Thank you for the many historic details. Who would have thought that you wrote this in 1.5 months? But I guess generally the positive outlook you guys express about the field, that's really refreshing to hear. Thank you very much. And indeed, if people have questions, please just go ahead. Maybe if I may, let me ask you one question. So an underlying goal of this, of course, is the measuring problem, right? So I mean, the fundamental idea that you don't want a Boolean answer as most of the time in verification, but you can actually compute something. And in a way, of course, the parameter identification is an indirect way of measuring, because you have this parameterized constraint, and then you look for the validity space. So on the one hand, this is very compact and very elegant. On the other hand, it is indirect, because the algorithm that computes these bounds is hidden from the specifier. Do you have a comment on this? What is the trade-off there between sort of the implicit way of describing the validity space versus the alternative would be in a programming language to actually collect the data, right? Like compute the maximum or compute the distribution and so forth. What are the trade-offs there?
So let me maybe I give one answer. I'm not sure whether this is a satisfactory answer, but I think in the way how we compute this validity domain, or how we represent it, approximate it, gives this kind of Pareto flavor, where you can you let the designer the freedom to choose like what would be the optimal concrete specification under multiple constraints, right? So it does not favor any dimensions of the parameter ranges. So then, if you would like to find what should be your concrete specification, you would need on top some kind of selection of what some kind of a policy of how you would weight different parameters in the parameter space. And The other thing that we assume here is that the engineer has a very good idea about the template of the property that he wants her or his system to satisfy. And this is also kind of key here, that you have this kind of declarative template that what is the property that you want your system to specify, and then you are looking in this parameter. So this constrains the parameter search space in a very specific manner. This is something that I guess just by doing using a program and computing a distribution would be harder to do. Alex, would you like to add or give an alternative response? Or Evgeny?
I would go in the same direction. Like there is this tension between computing the exact whole thing, which feels like an overkill, but just having this quantifier elimination expression that gives this huge set of constraints. That okay, we have the exact thing, but it's kind of too big. And this reminds me also of what we do with reachability analysis of hybrid systems, that we want to absolutely represent precisely everything that's reachable. But what we really need is just sort of when it's the portion that's critical for the problem that we want to solve. So there is this tension between giving something a complete answer, learning a complete answer, or just giving a few samples. But how do you give these few samples? And so what worked well in this paper is indeed this Pareto ID, which basically you say, if you have a compact representation of this Pareto front, and what we did with this monotony ID, we could represent this front with a few corner points, right? And so you have like a compact representation of that, and so then you can give a relatively useful answer that's a good trade-off, because you can say, okay, here is the front. Each of these the values on this front is useful in some way, and now it's up to the user or to the designer to choose how to use this front and which region of this front to pick, right? So to be more concrete, this front is going to give you amplitude, like the values in domain, like x greater than p, so you give you values for p, and time domain. So do you want to privilege urgentness, or do you want to privilege amplitude or distance, search distance? And so you have this whole front to pick from, and very much like you do when you're doing design engineering, you have a range of options, and you pick on one corner and the other corner. So you privilege amplitude on one side, but still want a minimum urgentness, or you want it to be very reactive. And so in that sense, and so it's true that this PSTL formula that we had there allowed to do this, but when we go to more complex templates, then it's I think it's very much one of the main issues in this whole learning, specification learning, mining, etc. Like how do you define the domain where you look for a solution that's going to present the user with useful options that he can pick from, not too rigid and sufficiently rich so that you can pick the useful answer. I don't know if this answered your question.
Thank you very much. That was a comprehensive answer. Are there more questions or comments? I guess that's not the case. So let me thank you again for this wonderful presentation. Congratulations again. I'm sorry.
Thank you.
And yeah, thank you again. And I don't know, Dana, Lou, do you want to take over?